Welcome! In this explainer, we're going to demystify some of the core ideas of linear algebra, and we're going to do it by thinking like an architect. We'll build our entire understanding from the ground up, using vectors as our one and only building material.
So why do we even need this stuff? Well, to see why, let's start with a problem. Meet Pablo. Pablo is a nutritionist, and he's trying to design a lunch program for a school. He's juggling all these competing demands, Parents want one thing, janitors another, fruit growers something else, and he has to keep sugar levels low. These are all constraints pulling in different directions. To find the best possible solution, he needs a system, a language to map it all out. What he really needs is the language of linear algebra. And today, we're going to learn the grammar.
So here's our blueprint for today. First, we'll look at our basic materials. That's vectors. Then, we'll see how far they can take us with this idea of span. After that, we'll figure out how to make an efficient design using independence and basis. Then, we get to the fun part, the actual construction of lines and planes. And finally, we'll check out a cool tool called projection, which is kind of like casting mathematical shadows.
Okay, first things first. Before any architect can build anything, they have to know their materials inside and out. For us, that fundamental building block, our brick and mortar, is the vector.
So what is a vector really? The easiest way to think about it is just as an arrow in space. That's it. It's a simple instruction. Go 3 blocks east and 4 blocks north. It gives you a direction and it gives you a distance, or a magnitude. These are the bricks and beams of our entire mathematical structure.
So we have our materials, our vectors. The next logical question for any architect is, okay, what can I actually build with these? What kinds of spaces can I create? And this is the fundamental question, right? If I have a set of building materials, how far do they reach? Can I build a simple line, a flat floor, an entire building? This very question leads us to an incredibly powerful concept in linear algebra of vectors span. The span is basically the total reach of your vectors. Imagine you have a few of those arrows. The span is every single point in the universe you can get to by stretching them, shrinking them, even flipping them around to point backward, and then adding them all together, tip to tail. It's the entire world you can explore using only those initial directions. Just look at this. You've got vector u and vector v. By taking some amount of u and adding some amount of v, we can literally land on any point on this flat surface that they create. Their span isn't just a couple of lines, it's an entire two-dimensional plane. Now, a good architect needs an efficient blueprint. They don't want to design with redundant instructions or wasted materials. And that brings us to the rules of our system, which make sure that we build in the smartest, most efficient way possible. So, how can we describe a whole space using the absolute minimum number of instructions? For an architect, this is all about saving materials. For our friend Pablo the nutritionist, it's about finding the simplest set of rules for his lunch plan. The goal here is to eliminate all waste. This brings us to a beautiful idea, the principle of no wasted directions. It's formally called linear independence. A set of vectors is linearly independent if every single one brings something new to the table, if each vector points in a direction you couldn't already get to by just combining the others. And this slide just lays it out perfectly. On the left, you have a dependent set. It's like having directions for north, east, and northeast. Well, that northeast direction is redundant, right? You can already get there by combining north and east. The independent set on the right is much cleaner. It gives you only the essential info. North and east, no waste.
So when you find that magic set of vectors, the ones that have zero redundancies, meaning they're linearly independent, and their reach covers your entire space, meaning they span the space, you've found what's called a basis. A basis is the architect's perfect blueprint. It is the smallest, most efficient set of instructions you need to build your entire world.
And this is the real power of a basis. It's not just a neat theory. A basis gives us a coordinate system. It lets us assign a unique address, like a column of numbers, to every single point in our space. This is the crucial bridge that turns these abstract geometric ideas into concrete numbers that a computer can actually work with.
All right, time for the construction phase. We have our efficient blueprint, our basis. So let's see how this actually builds our geometric world, from simple lines all the way up to entire planes.
The logic here is just beautifully simple. Let's start with one vector, just one building block. What's its span? Well, if you can go forwards and backwards along that single direction, you create a line. Easy enough. Now, what if you take 2 independent vectors? As we saw before, their combined span creates a flat surface, a plane.
So to define a plane in 3D space, all you really need is a starting point. Think of it as the foundation of your building. And your basis, those two independent vectors that act as the framework. Any point on that plane can be reached simply by starting at your origin and then traveling along some combination of those two basis vectors. And this is the actual architectural formula for building that plane. It might look a little mathy, but it's really simple. It just says that to get to any point on the plane, you just start at your starting point, then you travel some amount a along your first vector, and add to that some amount b along your second vector. That's it. Every point is just a unique recipe combining those two directions. Okay, so we're great at building flat things. We can build planes, but what happens when you have a point that's, well, not on your plane? Let's say you need to find the shortest possible support beam from that point straight down to the floor. This means you have to find the closest point on the plane, and for this, we need a new tool, projection.
You know, the absolute best way to visualize projection is to think about shadows. Imagine you have a vector, just an arrow sticking out in space, and you have a flat plane underneath it. If you shine a light from directly overhead, the shadow that vector casts onto the plane is its projection. It's the part of the vector that lies perfectly along that surface.
Now, here's a simple but really profound idea. Once you've already cast a shadow onto the ground, what happens if you try to cast a shadow of the shadow? Well, nothing. It's already on the ground. It's like being on the ground floor of an elevator and pressing the ground floor button. It doesn't do anything. And algebraically, this simple idea is written as p squared equals p.
Okay, I know this might look intimidating, but just think of it as a machine. The matrix A is where you plug in the blueprints for your surface, your basis vectors. This entire formula then creates a special processor, this matrix P. You can feed any vector in 3D space into this machine, and what it spits out is the exact location of that vector's shadow on your surface.
So if you ever want to spot a projection matrix out in the wild, you just need to check two things. First, does it follow that shadow of a shadow rule, where p squared equals p? And second, is it symmetric, meaning it equals its own transpose? If it passes both of those tests, congratulations, you found a projection matrix. Those two rules are its complete identity.
So we've gone from simple little arrows all the way to building entire planes and casting these mathematical shadows. But this toolkit isn't just for building geometric shapes. It's the same language that helps solve problems for nutritionists like Pablo, for video game designers, for data scientists, and engineers. It gives us a way to describe and solve incredibly complex systems. So the real question is, now that you speak the language, what are you going to build?